TechSpot. How do you feel? Perfect. Perfect. Thank you all for coming today. I hope that you managed to grab some drinks, food, and you feel comfortable and happy. For those who are watching us online, I hope you're feeling good. Also, and so thank you that you decided to join us today and to spend this evening all together. The topic that we're going to dive today is quite specific and not that much people are into it. So people that around you are those who are, let's say, like-minded people. Please go ahead and talk to each other. Yeah, we are a TechSpot. It's a community of software engineers, and we gathered. We decided to come together in order to learn, in order to dive into interesting topics, and we're doing it with the support of On the Spot. Thank you, On the Spot, for driving and supporting us. And actually, that's how even this meetup was organized. On the Spot is a company that is building offshore development offices for tech startups. And in order to be expert, we invite speakers from top companies to learn from them. And that's why today we're having Anna and Dylan from Isovalent. So as every community, we have a couple of rules. The first is to be nice, friendly, and curious. We are from different backgrounds, different countries here, and I invite all of you to make sure that people around you are involved, that no one is left behind. Please own your own stuff, starting from some precious things you have with you, and also like mind your bottle. Don't leave it somewhere. Make sure that you drink it and put it into a trash. Don't be shy, because for the best questions, we've got prizes. It's the super cool on-the-spot mugs, and yeah, so don't be shy. Raise your hands and ask the questions. And a couple of org details. If you want to have a coffee, please do not turn on the coffee machine during the event, because it's too loud. It will disturb us. Please do not go over our artificial walls over there, because behind them there are people are still working. Yeah, a good one. A good one. In order to be slides, help me. Yeah, in order to be curious, you all saw the cybersecurity bingos, right? How do we place them? The goal of the bingo is to find at least 8 people who can tell these statements about themselves. So you need to find at least eight people. The first one should have the same password for many accounts. Another one should open and click on different Nigerian prince emails. Once you got it, you just shout out bingo, and you also receive our on-the-spot mug. So have fun, find people, network. All the photos, recordings will be here on LinkedIn. If you want, you can scan this QR code. Yep. Take your time. What's the slides? A very important thing is that something wrong with the slide. Okay. Anyway, after the event, we're going to a beer to continue the party. And we invite all of you to join us. Speakers will be there. It's a chance to talk to them without any formalities. It's 10 minutes walk from here, so we gather after the event and all are hitting there. Yep, we are ready to start. And I'm happy to welcome our first speaker, Anna. Welcome.
All right. No, it's not switch on. Is it switch on? Can you hear me? Is it on? Yeah. Okay, great. Thank you, Katya. All right. Hi, everyone. Glad to be here and glad to that you all are here and that we can meet tonight and chat about eBPF. I'm Anna. I work at Isovalent, recently acquired by Cisco. But I don't think I must repeat it every time. So yeah, I work at Isovalent on observability tooling for networking and security use cases. So Isovalent uses eBPF very heavily for networking and security. I work on observability products on top of that, and I'm responsible for making sure that these projects integrate well with the whole observability and Kubernetes ecosystem, which is so big these days. Yeah. Today, I'm going to talk about Tetragon. So Tetragon is the main project I am focused on at the moment. It's an observability and security tool using eBPF, of course, and focus on the cloud-native Kubernetes ecosystem. So without further ado, does it work? Oh, yeah, Tetragon. Tetragon is an open source tool. It's part of CNCF as part of sub-project of Cilium. And it is using eBPF mainly for generating events. The events are low-level events attached to a process. So it's monitoring processes essentially. And it does filtering, aggregation, and also enforcement for security in kernel. It is Kubernetes-native in a way that all events and all data produced by Tetragon has Kubernetes metadata about user workloads, so things like namespaces, workloads, spot names, things like this. And Tetragon is configurable via Kubernetes custom resources. Tetragon is a pretty generic tool, and at first it was developed like a few years ago as part of Isovalent Enterprise Platform. Now, Isovalent Enterprise Platform still uses Tetragon, like the open source project, and kind of builds on top of it. Because Tetragon is so generic, you will see examples in the next slides. There are many things you can build with it. You can use it for observability and security, like just as a tool you install, but we see more and more projects that more and more people actually building some projects on top of Tetragon, and we essentially do it too at Isovalent. We built a platform that uses Tetragon and adds some advanced features to it. By advanced features, I mean mostly internal network parsers for all popular protocols, both layer 4 and layer 7, so TCP, UDP, HTTP, DNS, and also file integrity monitoring. We also, in the platform, we also try to provide users this sort of out-of-the-box experience. So experience where you install Tetragon, install the whole platform, and you have security and visibility for your needs, for example, your compliance requirements. So we provide default security rule set. We provide UI in the form of dashboards mostly, and integrations with various CMs and popular observability tools. If you want to learn more about it, then feel free to visit the website. All right. So this is a picture that I took it from the front page of Tetragon documentation. There is a lot of going on here, so I will kind of dive into it and into different parts. So first, Tetragon is very generic tool. I'm saying it for the 5th time now, I think. It is, at its core, it hooks into kernel events and produces events, monitors what happens in the kernel, but it can hook into practically any kernel event. And because of that, it can be used for many, many, many different use cases. Some of the most popular ones are process execution and also syscalls. This is the core functionality of Tetragon because all of the events have this process context, like there's some process running and everything is attached to this process. Network activity, network connections, and network traffic, disk and file access, and some Linux-specific security things like changes in Linux namespaces and capabilities, which are source of some common popular, some known CVEs that were like very covered by media in the recent years. All right. Then we have eBPF. So I'm not gonna dive into eBPF very, very deeply in this talk. I will mostly talk about how we use it and our experience, our learnings on the way. But something I wanted to highlight is why Tetragon even uses eBPF. The major thing is that, well, Tetragon is originally developed by kernel developers by BPF maintainers. But what are we getting from using eBPF? We are getting reliability. And this is something I feel is a bit underappreciated when we talk about eBPF, especially in observability context, because many people appreciate that eBPF provides observability with no instrumentation, or that it provides observability with very low overhead. And this is great. This is absolutely great. But this reliability aspect is not really appreciated that much, and it should be, in my opinion, because many of us experienced some dreadful incidents that, for example, affected some sidecars that were collecting telemetry, or many of us have installed some tools that were supposed to provide us observability, and these tools started crashing, and this also affecting the applications running in the nodes. This is awful, and eBPF doesn't completely solve this problem, but because eBPF programs are verified by eBPF verifier, they are safe to run, and they are more reliable than most software we write. They are not bug-free, no magic there, but they are pretty reliable. They provide complete visibility. This is especially important in the context of security observability, because security teams don't like when you tell them that, oh, by the way, we might randomly miss some events. No, they don't want to hear this. They want to have complete visibility, be sure that you don't miss anything, and we can achieve this more reliably with eBPF. And doing in-kernel enforcement, this was tricky, but this is also a very, very powerful thing, because doing enforcement in kernel means that we are essentially more secure. We are protecting against much wider range of attacks, because we don't have to trust user memory. And this is very, very powerful. eBPF provides us with low overhead. This is a matter of thing for Tetragon. We are trying to develop it in a way that it keep the overhead to the minimum. So yeah, BPF programs are generally fast, and major thing that allows us to achieve this low overhead is that we run it in kernel. We don't have to switch back and forth between kernel and user memory. And we also do both filtering and aggregation in kernel, so we can kind of process this data very, very efficiently. Not, we don't have to send it over and over through a few services to kind of filter and aggregate it as we would do with some other tools. Next thing, the agent. So Tetragon has the BPF part in kernel and agent in user space. The agent can run on any Linux and it can run in Kubernetes. Here I will focus on the Kubernetes part, but it can also run on bare metal. It can run as a container or just as a binary managed by systemd or whatever. It can run on any Linux, essentially. The difference is in how you configure it, because when running outside of Kubernetes, of course, you don't have access to all these Kubernetes custom resources, etc. Tetragon monitors user applications, and user applications can be written in any language, can use any framework. Tetragon will see them. This is not to say that eBPF doesn't care about the programming language that application is written in at all. It depends on what you are doing. Sometimes it is relevant, sometimes it is not, but the eBPF programs will see what the application is doing, no matter what language it's written in. And many or most Tetragon use cases are really language agnostic. To monitor applications, we don't have to make any changes to their code or to their configuration, of course. And we also don't have to even restart them or install anything alongside applications like any sidecar or anything like this. The applications just keep running like they were running forever. When we install Tetragon, then Tetragon will just see them without affecting them in any way. And the last bit, integrations and data pipelines. So Tetragon is very low-level tool which generates events in the kernel. And what then? This is a part that, this is essentially my job. This is what I'm focusing on, integrations with the all very big observability and security ecosystem. So Tetragon events can be forwarded to any security, any CM system like Splunk and Elastic are, I think, some of the most popular ones. Any observability tool that collects metrics or logs. In Kubernetes world, this is usually Prometheus, Grafana, and recently more and more OpenTelemetry. And what many organizations choose to do is to actually build something on their own, to forward the Tetragon events, for example, to AWS S3 or to ClickHouse, and build some queries, some visualizations using this storage. We also developed a tool based on ClickHouse internally to efficiently query these events. All these integrations vary in maturity stages, but you can do whatever. There are a million ways to do it, really. All right. All right, what happened to the slides? Okay, this. Can you go to 9, please? Okay, earlier, I think it skipped a lot of slides. Okay, here, yeah, thank you. All right, this is here, thank you. I don't know what I clicked, but sorry about this. All right, now I wanted to talk a bit about what we learned during the whole process. So Tetragon has a few years, and we've been running it with our customers on pretty large scale already with very high compliance environments. And we learned a lot of lessons by working closely with our customers on this production deployments. The first thing is that in-kernel state is powerful for context and avoiding races. And this is a core component of Tetragon are, of course, the BPF programs. And BPF programs use BPF maps for the state, essentially. So we have a few kinds of BPF maps. All of them are essentially some kinds of key value stored in kernel memory. There are many different kinds of BPF maps in general. In BPF, we are using them for a few main things. We store all the processes that we saw we call it exec map. Then we saw sockets that were open in socket map. Then we have Masa maps for files and for Kubernetes metadata. The Kubernetes metadata part is what is really powerful because we get this Kubernetes metadata from container runtime. Actually, I won't dive into it, but yeah, we could get it from Kubernetes API, but for security reasons, we switched to retrieve it from container runtimes. Anyway, my point is that we get this Kubernetes metadata in user space. We write it from user space to the BPF map. And then when we are processing events in kernel, we don't have to reach back to user space anymore for this Kubernetes metadata. We just read it from the map. Similar thing applies for processes or sockets that were started before Tetragon started. We can retrieve them and just store them in a map. The next thing is that in-kernel filtering and aggregation are really essential for low overhead. And how observability pipelines usually work is that we collect lots of events, lots of metrics, and then we always somehow filter and aggregate them. It happens at various stages, and sometimes there are many tools involved, but often we are just sending lots of data between many different services to do this. Doing all of this, not only in one service, but just in kernel memory is really, really powerful and allows us to provide this low overhead. So yeah, when we benchmarked the initial versions of Tetragon with customers, that we found that we found some common biggest performance issues, which was completely unsurprisingly the volume of data, because Tetragon can observe so many things. It is very, very, very easy to just produce some insane amount of data. But when developing some filters and aggregating data, we could actually make Tetragon very efficient. So yeah, here are some benchmarks. We are benchmarking Tetragon, let's say, semi-regularly. If you are interested in numbers, you can read the blog post announcing the Tetragon 1.0 release. There are some detailed benchmarks that I showed here about the overhead for Tetragon. We are generally trying to keep the overhead 2, 3, up to 5%. This is what seems really, really good and compared to alternatives. A kernel is more than syscalls. So when eBPF is introduced to people, often it is associated with syscalls, that eBPF programs are attached to syscalls and to something. And yeah, of course, eBPF programs can be attached to syscalls, but they can be attached to many different things. And many Tetragon use cases actually don't attach to syscalls for various reasons, but attach to some underlying kernel function, to kprobes. And this being that generic and digging deeper into the kernel, attaching to kprobes, not syscalls, is what allowed us to serve so many use cases and also provide such a reliable experience. Threat models include bots, containers, apps. Okay, so now I'm gonna dive a little bit into the security part of Tetragon, because Tetragon does observability and security. Observability mostly in the security context, and there are a few things that are very popular in observability tools using eBPF that we chose not to do. We chose not to do them because Tetragon is a security tool in the first place, and these things are not secure and as we would like to. And this includes uprobes. So uprobes are great. Uprobes uprobes allow you to attach BPF programs to user space functions. And this is great in observability tools because like the user observability tools are mostly interested in user functions, right? When you want to observe your application, you want to observe what functions in your code do, not what some obscure kprobes do. And uprobes are great for observability, but from the security perspective, they are problematic because they are in user memory. You have to trust the user to not manipulate them. And when we are building security tool, we don't trust user space. We are assuming that user space might be compromised and controlled by an attacker. Syscall user pointers. This is a similar situation. We actually, for many use cases where we could use syscalls, we don't use syscall, but we use some kernel functions that is under the hood called by the syscall for this reason that we don't want to compromise user memory. We assume it might be controlled by an attacker. And yeah, the one major thing we learned is that the difficult part of eBPF is really finding where to attach. Because we can attach to anything, but often finding the right function that will work reliably on many Linux distributions and that will provide us data we need is really the difficult part that requires kernel expertise. Next thing is enforcement in kernel on top of visibility. So as I mentioned, Tetragon provides enforcement in addition to visibility. There are a few ways that we do security with Tetragon. The first kind of most obvious and the easiest thing is audit. So we collect a lot of events and then store them somewhere, and then security teams can query them for audit. So query some. If everything was all right. There's alerting. So alerting is a more synchronous way of doing security, where when we detect something that is suspicious, and we, for example, some known CV being executed, and we alert user, and the user can immediately look into it and mitigate the security vulnerability. The thing is that this user action happens when the attack might have already been successful. And the sort of next stage is enforcement, where we solve this problem, we actually block the attack instead of just alerting user and telling user to do something with it. So in Tetragon, we block the attack, and we just tell the user that, hey, we blocked it. And this is difficult. This is difficult because there are very many things that are tempting to do, like send some event and then from user space, kill the process, whatever. These things don't provide good security model because they rely on us trusting user memory, and we don't want to do this. So enforcement in Tetragon is done entirely in kernel, and this is also a thing where we have to be careful when we integrate with things like Kubernetes, because Kubernetes is distributed system. Kubernetes is designed to be run at a very large scale. But the enforcement bit happens in the kernel, and it can't rely on the whole entire Kubernetes system being in good state, because this very, very often isn't the case. In Kubernetes things go wrong all the time, and Kubernetes just deals with it. So the enforcement bit, we have to kind of separate this giant distributed system from the kernel, and this is why we, for example, get Kubernetes metadata not from Kubernetes API, but from something local from the container runtime. Okay, it's happened again. I think it doesn't like this dark slides. No, really, it's the thing. Okay, it's not that this dark slide. Okay, we will see. All right, so now I wanted to show a little bit of Tetragon, like configuration and internals, how Tetragon is configured in Kubernetes. So how you can use it when you are not a kernel developer. Tetragon in Kubernetes is configured via tracing policy custom resource, which looks like this. Tracing policy, and we define which points we want to hook into. In this case, we hook into 3 kprobes: TCP connect, TCP close, TCP send message. So these are kprobes for opening, closing TCP connection, and sending something over it. It looks like this. There is more configuration for filtering. So we can filter what events we want to get, for example, by Kubernetes metadata of the application. So for example, we want to monitor network activity only of this Tetra demo application in this case. And this configuration that I have over, this configuration that I have over here will be stored in a eBPF map. And there are many other things that we can actually filter on than Kubernetes metadata. For example, we can essentially filter by like arguments of the kernel functions. And in this case, we filter by IPs. So this is example where we want to monitor only external traffic external to the cluster, connections external to the cluster. So here in the list, we put pod sider, services sider, and localhost. They will be ignored, and we'll get events for everything else. This sort of policy is very useful, for example, for air-gapped environment. We have some users like with high compliance air-gapped environment when they don't allow any external traffic, and then you can write a policy ad like this and alert if you see any event produced by it. Okay, so this was YAML, and just because I like showing C code on slides. I will now show how it's implemented. This is the only slide with C code, so there won't be more of it. But this is the actual BPF code for Tetragon implementing this IP filtering. It's very heavily truncated because to fit it on the slide essentially. But this is the code. So essentially get this. Get IP that is going on through the network stack. We do some map lookups here and here to check if this IP matches the configuration which was previously stored in BPF maps, and then we return whether we should ignore it or not. All right. So I said a few slides earlier that I will show how to configure Tetragon if you're not a kernel developer. And this configuration, well, it didn't look like this, right? Like kind of to write something like this, you have to know what this function do exactly. You need to know which argument in what function holds the IP address. Writing this requires solid kernel expertise, honestly. And so to make Tetragon accessible for the rest of the world, we develop sort of a policy library. So the Tetragon team has a few kernel engineers who actually write these policies a lot. I'm not one of them, but there are a few people who know all these kind of functions in details and can write the policies. And we have a policy library in Tetragon documentation and also examples directory in the Tetragon repository. So the examples are sort of community maintained. There are many tons of different policies for different use cases. There are some policies for example, CVEs that you might have heard of. And the policy library in the documentation is sort of a curated list of policies that are recommended for some environments. So yeah, this is you can just take policies from there and install them. All right, advanced use cases which we develop at Isovalent in the enterprise platform are mainly in kernel parsers for network protocols, which are also configured via tracing policy. So you just define which network protocol you want to observe and just enable it. You can also enable what telemetry data you want to get for this protocol. So for example, events or metrics or both. And you are just getting it. So all of this will enable some, we call them sensors, which are essentially like collections of BPF programs that get loaded, and these programs are parsing some protocols, for example, HTTP DNS, and produce events for traffic for these protocols, so that we have, for example, not just IPs in TCP events, but DNS names of the destination, or we have all HTTP statistics like golden signals, so latency, errors, duration, HTTP, all metadata from HTTP. So this is what we are developing, and to make the setup easy, we also are developing the default rule set, which by default, I mean, it's recommended for most of the users, where it's essentially a set of policies for monitoring operating system integrity, for monitoring containers, some suspicious network activity, and to make it easy to install, we just put it in a Helm chart, and that you use to install Tetragon in Kubernetes, and with one Helm value, you can just enable this default rule set. All right. Oh, it worked this time, dark side. So this was Tetragon configuration, and now Tetragon produces events so far I didn't say what an event is. Yeah, I will say it now. Tetragon produces some telemetry data, which then is processed somehow in a data pipeline. There are a million ways of doing it. But yeah, one of a thing that we show in demos, for example, is Tetra CLI. So Tetragon comes with Tetra CLI, which you can use to query events. You run inside the Tetragon agent, you run Tetra get events, and you get, for example, these are events for the policy, the TCP policy I showed earlier. When we see the TCP connection opened, a TCP message sent with bytes count, and TCP closed. This is it. So yeah, this is for demos. What is used in production more often is actually events in JSON format, and Tetragon events look like that. They are pretty wide JSON, where here we can see only part of it, but here we can see like process metadata. So Tetragon events are associated with a process, and for each process we can see all the Linux details of this process. So like what was the binary executed, its argument, process ID, start time, and also Kubernetes metadata. So in this case, this is event for Cilium pod running in copy system namespace. So we have these JSON events which are stored on disk in a file. And this is pretty simple. This is super simple, actually. Like we just store JSON events in a file like a regular log. And this is what actually allowed us to run Tetragon at very large scale in high compliance environments while having very small team, just a few kernel developers doing this, because what you do with these files, with JSON events, is that you build a pipeline that is exporting them somewhere and then querying and visualizing these events, right? In Kubernetes world, this usually involves some logs collector, so something like Rendiff with Bit or OpenTelemetry collector, and then the events can be exported to any tool that collects logs, like regular application logs. So Grafana Loki is a popular one. More security-focused tools like Splunk or Elastic, and many people decide to build something on their own using, for example, ClickHouse or some AWS services. This thing is absolutely in no way specific to Tetragon, right? Like most applications do some logging in order to standard output to a file, but then there's a collector collecting logs, and then there's some storage that's where you query and visualize the logs. Because we kept Tetragon that simple, that it's just produces JSON events and stores into a file, most users who have something like this already in place, which means any medium-sized or large organization can just reuse their pipeline and to process Tetragon events and do something with them. Yeah, so this is what happens to events. Tetragon produces also metrics, Prometheus metrics. And this is how we do Prometheus metrics is a little bit different than most tools do it because we do eBPF, right? So we collect data in eBPF, aggregate them in eBPF, and store them in maps. How metrics are usually, how Prometheus metrics are work is that we collect the metrics, we expose them somewhere, and then Prometheus or some compatible tool scrapes them and then stores them, and then we query and visualize them, for example, using Grafana. These first two steps usually are one step we just call instrumentation, right? That we instrument application to collect and expose the metrics. But because we use eBPF and aggregate data in eBPF, we sort of separate these two steps. So the collection part happens in the kernel, and the Tetragon agent does only the exposing part. Tetragon agent reads metrics from eBPF map, and when Prometheus scrapes them, and just sends to Prometheus. And keeping it, this of course reduces the overhead, because we still we still have to store the metrics, just not in a user, but in kernel memory. But but we kind of don't. We can store only what we need to. Okay. So now, how much time do I have left? Okay, 5 minutes, not much. Great. So I wanted to go quickly through some use cases, main use cases for Tetragon, and I will just go through some slides showing some visualizations that we work on. Our visualizations are mostly dashboards, either Grafana or Splunk, because we don't have dedicated UI team, and this is how you do UI. If you don't have dedicated UI team, you just do Grafana or Splunk. So yeah, this is what we do. So the first basic use case is the process lifecycle. This is the core of Tetragon. Tetragon monitors processes, and this allows us to find many interesting things about what is happening. So we can, for example, use Tetragon to monitor privileged workloads and processes. Nobody likes running privileged workloads, but sometimes you have to. And because you always do, you want to monitor if you are not running any additional privileged workloads. So this is Splunk query for it. Don't pay much attention to Splunk queries. I just put them on the slides. But yeah, we can just query for Linux capabilities, and we get this information. They take late process execution. So late process execution is when we start, for example, Kubernetes-native, it starts up, and usually we just expect it to run after this. Sometimes what happens is that after, an hour or so, something extra starts, some extra process in the pod. And this might be expected, but very often this is unexpected. This means that something went wrong, or the pod was attacked. So we can also use the process start time stored in Tetragon events to detect this. Malicious shell executions. This is something. Shell executions are also part of many security attacks, and we can monitor malicious shell executions in Kubernetes cluster using this binary stored in the Tetragon events. We developed dashboard for this. So this is Grafana dashboards showing malicious shell executions. And we kind of tried, this is, we're trying to take this out of the box approach, where you can just install the dashboard and it will work in all environments. It's not easy, but we are working on this out-of-the-box dashboards. For example, for Linux capabilities and namespace changes. This is Splunk, not Grafana, but this is Splunk, like sort of audit dashboard that shows Linux capabilities and namespaces. Another use case is network visibility. So suspicious network activity is something, of course, every security team wants to monitor. We also developed these Grafana dashboards that can be used for many things. It can be used for security use cases, like as Tetragon was initially designed for, but these are actually also very, very useful for just monitoring network activity of the applications, because we have also bytes count, and also we can combine what we see on the network with, for example, files operations. this opens up really many interesting use cases when we can, for example, get very interesting information about what databases can do when we have all the bytes counts and all details about file operations. This provides very great insights into database operations. Yeah, so these are dashboards for, I think, TCP, latency, and like throughput. And TLS compliance is another network-related thing that's very crucial to monitor for most security teams. So to detect weak TLS ciphers, weak TLS versions, malicious or new domain names, and things like self-signed certificates. So again, like auditing things with such a dashboard is something that most security teams need to do. And data exfiltration. Something that we found out that many people are interested mostly in like external traffic when when using Tetragon, because external traffic is usually associated with first higher cost, like requests to a SaaS platform or external requests are usually charged more by cloud providers, so they are associated with higher cost, and also they are subject like to serious security attacks. A request to, for example, external payments platform or things like this. So yeah, so that data exfiltration is another example of this, where external traffic is something we monitoring, like the throughput to external URLs is something we are providing visibility to. And yeah, this is this dashboard shows us the like external external traffic byte counts. File integrity monitoring is the like last major use case. It's we also develop like out of the box dashboard that provides visibility into operations on sensitive files. Yeah, and we see here like file operations. So read, writes, deletes, all of these file operations, and changes to passwords, for example. This is one of the like main and sort of most obvious things we want to monitor when it comes to files, that nobody changes secrets that are stored on the disk. All right. So this was it to wrap up. To learn more, I put a few links here. If you want to learn more, then we have hands-on labs on Isovalent websites. There are not that many specifically for Tetragon. I think more of them are for Cilium, but there are some. So feel free to take a look and do the labs. They are pretty fun and like I think efficient way to try out without installing Tetragon in your own environment. There is an O'Reilly report written by my colleague that you can download from the Isovalent website for free for the price of your email, I guess. So yeah, check it out too. And on the Isovalent blog, we have detailed walkthroughs through several of these use cases that I just quickly shown. So things like file integrity monitoring or specific CVEs that can be detected and blocked with Tetragon are covered there too. So yeah, check it out if you are interested in some specific use case and deep dive into it. Try it out. And if you are interested in contributing to Tetragon, then it's definitely more than welcome. By contributing, I don't mean only writing code, but also we welcome. It's very helpful when you try it out, experiment with Tetragon, and tell us about the bugs or difficulties you found out, because Tetragon is such a low-level tool. It's sometimes sometimes it might scare people. So if you try it out and tell us what was easy and what difficult. This is super helpful. Tetragon repository is on GitHub under cilium organization, Tetragon documentation under Tetragon.io. In Tetragon documentation, you can also walk through a few of these use cases and the policy library too. And we have Slack. There is a Cilium and eBPF Slack, which you can register in. And there's Tetragon channel, so feel free to jump in and ask questions or share whatever you want to share. And in general, if you are interested in eBPF and want to connect with people using eBPF daily for many different things, then this is the right place to be. All right, this is it. Thank you very much.
Any questions so far?
Hi, thanks a lot for the presentation. Actually, I have 2 questions and a half. At first, is it possible to use Tetragon, the custom Linux kernel network stack based on data plane development kit, DPDK? For example, if we are not happy with performance for a default Linux network stack, we have a custom network stack, and we want to use a Tetragon with it.
Okay, I mean, if you mean like running Tetragon, it's I think the required kernel version for the core Tetragon part is 4.19. So this is required to have this process information. And then on top of that, if you want to use Tetragon for specifically networking use cases and you have a custom networking stack, it might not work. It depends on what you replace.
Internal Linux network interfaces, as far as I understand. Yep. Like internal interfaces, internal C structures, TCP, UDP, and something like that.
Okay.
Am I right?
Yeah, so Tetragon, networking features need this.
Okay.
Need this kernel structure. So for networking features, this might not work. But yeah, for other things, you can.
Is it possible to customize it?
I mean, you can write your own tracing policies, and tracing policies are very, very flexible to so that you can hook into whatever you want, and you can configure which arguments from the Linux function you will get in the events produced. So you can write your own tracing policies, and they should work. Just if you have custom stack, then you probably have to do it. Yeah.
Yeah. Thank you. Next question. What were the reasons to implement all this stuff based on eBPF instead of old but gold C kernel module or Rust base, if you like it, except flexibility in runtime, in changing and loading in runtime eBPF programs?
So yeah, flexibility is a big thing of this, but the problem with kernel modules is always that they can crash the kernel if there is a
eBPF
bug,
can
right?
too. It has vulnerabilities.
Well, eBPF it's much less likely.
Yeah.
Yeah, it's so with kernel modules, this it's just would be. I think this many of these things are possible with kernel modules. Just they would need to be really rock solid to be accepted by large enterprises to run. So developing a tool like this as kernel modules would be really much more difficult. And this flexibility is also a big thing that you configure Tetragon with, in Kubernetes, you configure with custom resources where just load them. You don't need to restart the agent, nothing. You just can unload different programs. So for example, when you want to just audit something in the cluster, you can load a few policies, check what you need to check, just unload them.
Did you try to perform some benchmarks between cKernel modules versus eBPF-based programs for your use cases, for Tetragon use cases?
We didn't run any such benchmark,
Okay.
so yeah, I can't answer this question.
And
but,
the last question, so if you have really a lot of filters for different protocols and so on, it can create a lot of CPU pressure. So even if you have a lot of, even if eBPF programs are fast enough, it can create a lot of loss to CPU. Yeah. And if you have a lot of eBPF programs, it can postpone execution of programs from user space. Is it possible to pin eBPF programs to a dedicated CPU core via a task set, a NumaCTL, something like that? Or maybe somehow tweak a CPU scheduler to share resources between user space programs and eBPF in some fair way?
Yeah, I don't know if it's possible, honestly. I never heard of it. So if somebody else knows, then please shout. I never heard of this being possible in any way. So I don't know. Yeah, that's a valid point that like we like to talk about low overhead very much, but if you create a ton of these policies, this of course will be some overhead, and it can, as you said, be also visible in user space applications because it slows down, like it takes CPU. This is just
Am I right that eBPF programs use the same CPU scheduler as regular processes? The same scheduler, the same algorithms inside the kernel?
I think so.
Okay. Thank you.
Yeah, so yeah, we don't monitor like overhead of BPF programs as well as we would like to yet, because I mean by overhead I mean CPU usage and memory usage of strict our BPF programs. Yeah, this is something we want to do, and we will do hopefully soon, because we of course monitor like the like overhead of the whole system, but having this information is would be really valuable. Yeah.
Yep. Thank you a lot.
You're welcome.
Yeah. Guys, sorry, we're out of time, and so the last question.
I'm lucky. Yeah, I saw a section on your presentation that we discussed the traces and collection of the traces, right?
Yeah, so we collect like traces it's an overloaded world in observability space. So, yeah, okay. But we collect like kernel traces. You know?
Yeah, but can I use those traces stored somewhere to troubleshoot my application, just to visualize latencies between microservices I host on my cluster, and in real time it will be the best. For example, to troubleshoot some active bottleneck.
Mm-hmm. So with what Tetragon provides at the moment, no. But you are not the first person asking about it, and we actually have discussed it, and we may have some sort of plan of it, because when it comes to like application traces, I guess you are mostly interested in HTTP.
Yes.
Right. So Tetragon does have a HTTP parser. This parser reads the HTTP headers, right? So the events have HTTP headers. And that includes trace headers. Having trace headers, we can produce and export trace spans. So this is doable. We haven't implemented this thing yet. I mean, we have the parser that reads the headers, so we need to implement everything on top of it. But yeah, hopefully one day, because this is you're not the first person asking for it.
Thank you.
Thank you, Anna.
Thank you.
So let's have 15 minutes break and get back to Dylan. Reimerink, also from Isovalent from at Cisco. So welcome, Dylan.
Let's see, does this work? Yes, nice. So, everyone's still enjoying themselves? Hope so. So, I would like to talk about eBPF loaders. I'm going to do a little quiz beforehand. Anyone hands up for anyone who knows what a loader is? eBPF loader. All right. Who of you has written any eBPF? Doesn't matter in what capacity. Hands. All right. Then I have a sort of idea. So, all right. Let me start. A little. Who am I? Thank you for introducing me. Thank you for inviting me here. My name is Reimerink. I work at Isovalent at Cisco. We add Cisco parts because we were recently acquired. I'm a Cilium contributor, part of the loader team and a foundations team. So my day job is I do a lot with loaders and everything that comes with that. So I also do a lot with our loader library, cilium/eBPF on GitHub. And I maintain my own eBPF doc. So if you ever wonder what a certain eBPF term is or something like that, then you can likely find it at my docs. So the only plug I will do for now. So before we get into the belly of the beast, what is a loader? So when you create an eBPF program, so focusing on the diagram, you first have to you write it in some programming language. C or Rust is an option nowadays. You have to compile that to get some bytecode, and that is for C. We end up with basically always we end up with an ELF file, and then whenever you are ready to actually start using your eBPF program, you have to load it into the kernel. And that is typically done by either a dedicated program for the job. So the IP command or the TC command actually have functionality to do this loading for you. We have a BPF tool, and BPF trace actually does it dynamically creates its own programs and it loads them. But you can also write your own loader with a loader library like libbpf, which is probably familiar for some of you, or eBPF Go. IA is for Rust development, and BCC is for people who want to use Python. But BCC also does little dynamic compilation, etc. So the loader is the part that actually makes the syscall, and that does actually quite a lot that you wouldn't know if you only ever use it from an API perspective. So I have a very simple program. So it's an XDP program that just collects some flow information, so some bytes and packets for destination, source and destination address. And I couldn't fit it all on the page, so I have a little forward declaration there, but we'll get into that. So this is our C program, and then we compile it. So what I have here is any normal C programmers will know the above command. So just clang output something, and then we get an executable out of it. You give it permissions, you execute it, and it's hello world. But when we use the BPF equivalent command, which is a little longer, if we actually get a relocatable, that's because I didn't use because the way BPF works. And I can't just execute this. It will say, nope, no, not for you, because in comparison, an executable is the pre-made closet on the right, but with BPF, we have the IKEA, we get the IKEA packet, and you have to do some assembly still, which is what our loader is for. So this ELF file looks something like this. So this is for my example program that I showed before. So we have the ELF header, which is at the top. So that is how our file command knows that it's an ELF. And then we have all of these sections, they're called. And every section has some unique form of information. So you can see that every section has a different format, and their formats are all based on convention, typically on the names or special flags that they have. So this is what we are presented with, or what the loader is presented with from a user. But what the kernel wants is this, the syscalls. So I seem to be missing a bit of the documentation. Anyway, so it's the man page of the man page for BPF, and this is basically the whole API from the kernel side. So what we have is we have a BPF syscall, and the only thing you provided this very big attribute structure. And what you'll find is that it's a union. So, and every command has its own field. So basically there are like a bunch of structures. Every command has its own fields that you want to provide. And that's how we communicate. There are actually 36 commands as of kernel 6.8. I believe they're not normally adding more, but you never know. So most of them are actually for like CRUD operations on maps. So maps for the non-initiated are the data structures where the kernel stores everything, or where eBPF programs store everything. But we can actually interact with those from user space as well to read what is there, to iterate over them, and do interesting, more advanced things like freezing them or binding them to specific programs. Of course, we need to load, attach, detach programs, which isn't always used. We'll get to that. We can run them, query for their existence. BTF, we'll get to what BTF is. Links, we'll also explain those. And some pinning and other operations. And like most of them are, again, for like querying, like listing whatever, which programs are currently loaded in the kernel and stuff like that. So these are normally, like every one of these are normally wrapped by some nice function in your programming language, but then the loader will translate these down to syscalls for you. So you can, in most libraries, like use them directly. For example, libbpf, or there might be like higher level APIs that just say, do something, and then it translates into like a bunch of these. So where this is again my program, and what you'll see in eBPF programs is that there's this sec macro on the top, and this tells the compiler to put this code into a specific elf section, and this is an eBPF thing. People decided to use the section name to give hints to the compiler on where to load a program. So in this case, I say because it starts with XTP, I'm telling the loader, hey, you should load this to. This is an XTP program, and then it will use that later on. And then we can inspect it. So I use LLVM object dump here to actually dump the contents of this. So we're going a little bit deeper already. And this is what we actually get out of our compiler. So it's a very regular pattern. Every BPF opcode is always 4 bytes? No, sorry, 8 bytes. We start with an opcode. So that's why it's in this very regular pattern, by the way. So we always have an opcode. We have source and destination registers for like moving things from register to register. We have an offset, which we use to jump relatively within the code, and we have an immediate value, which is by default 32 bits. So to set some value in a register, like to an explicit value, but there's also this neat trick where sometimes we use two instructions together and we just do that to get a 64-bit number, so we then can combine the immediate values from two instructions. So this is like what we get, and this is this is like the almost the thing that we might want to give to the kernel, but we have to do something. So we can also, instead of just dumping the bytes, we can ask it to actually decompile this, and then we can see the instructions on the right. And what you'll notice is that there's this call instruction with a -1, and its source register is set to 1. But that's strange, right? Because there's no source for calling a function. And this is actually a hint to the loader that, hey, we need to do something here. This is where we're missing a bit. And the reason it's here is because I'm using I'm doing a function call. And in BPF nowadays, it's supported to do like function calls. We call it BPF to BPF functions. but the loader needs to do a little bit of work to make that happen. So what happens is we had the instruction that was missed that had this -1, and then when we have the section which starts with .rel, it's the relocation entries for that section, and then at a certain byte offset, we have a relocation for our handle IPv4 function that we forward declarated. Now, if we look up the symbol table, then we can see that this symbol actually can be found in the .text section, which is where the compiler will normally put all of our executable code if we don't explicitly set a section on it. So all of our shared code, basically, not our entry points, but the other functions, if they're not inline, they end up there. But when we look at all of the information we can provide to the kernel for our program, we only have one pointer for our instructions. So we need to assemble this. So let's say I had two programs and they shared some features. So this would be how it would look in our file. We have like some functions, we get our entry points, but then we actually need to assemble them into the following two things. So we need to figure out which functions are actually used, then make blobs of the code where the functions that are actually used are appended, and then we can resolve the relative addresses, so we can relatively jump to these functions, and that's different. So this is something that a loader does for you whenever you use something like this. And actually similar thing happens with maps. So we define a map, we have the same thing where you have a key, a value, we define what it is. And here we have the same macro again, the sec macro. So what we do is instead of putting this in the default place, we put it specifically in .maps because .maps has significance for us. And the way it's used is that in the function, what I specifically would like you to look at, I didn't highlight in this case, but is the map lookup element. So here we have a pointer to this flow map, which was a globally defined thing. But then if we actually go look at the code, then this is an example of the 64-bit immediate, so where we use two instructions at the same time. And here should be the memory address of the map, but it's not there. And actually the reason it's 64 bits is because the kernel is going to, whenever we give this to the kernel, it's going to reuse the exact space here to put an actual 64-bit memory address there. But we don't have to bother. We don't have the memory addresses of where the actual map would live in kernel memory. But we have to provide it something. So what we, again, do is we go look, we have relocation entries for exactly these instruction points. Look up where is this in maps. Cool, that must mean that we need to put a file descriptor for a map here. So whenever you define a map within your code, it's not actually your code that is creating it or whatever, but it's a very indirect hint to the loader to create that map for you and link it to your program right before the program itself is loaded. Creating a map is also, again, its own opcode with a lot of type information. And these are derived from whatever you put in there, like the map type is here is on the top and the size of your keys, but also some other things that I don't have time to explain all of them. So you would think, cool, so that information must be in the same way it's in the, or must be in that section then as well. And then you go look and it's 0. Why? Well, the reason is, if you look at the struct, is that this is actually the definition of the type, but we never assign any values to it. So everything is 0. Now, in the olden days of the very early version of eBPF, maps actually used to have this very specific struct definition, and you actually did provide values of the maps, and they would go in the maps section, not the .maps section. But this is deprecated, long not used anymore, and now we do it this way, and it's called BTF maps. So before I can explain then how we actually can use this information, I need to explain what BTF is. BTF is BPF type format, so it's like all of the type information. What does my structure look like? Is it a pointer? Is it a number? Whatever. Like all of the type information is in there. And the reason kernel developers decided to create this is because it's way smaller than dwarf information, which is like the default information that you would use for a debugger. But we still derive it from dwarf. So there's tooling that can turn all your normal compiler outputs into BTF and so on. Why do we need this? For a bunch of reasons. One of them is the maps. We have spin locks, callbacks, a lot of other advanced features where the kernel actually, for example, wants to look inside of the map to see that if you want to use spin locks on a map, it needs to make sure that it knows where in that map value you have a spin lock. Do you actually have a spin lock in there? So it uses this type information to do very strict validation, also so that you actually did what the compiler what the kernel wants you to do. So it's just like providing additional information on top of just the bytecode. It also allows for flexible map attributes like we have. I'll explain it in a bit. It provides additional debug information and so on, and core, also deferred for later. But what is important to remember is that by default, for example, in Clang, you need to actually always compile with the -G, which means that it includes these debug symbols in there. So a lot of people at first get confused, like why doesn't this work? And they just forgot to add the debug symbols, and because it's not something you would have to do in non-eBPF programs. This BPF looks something like this when you inspect it. So there's a lot of information here. And what I would actually, so an actual focus of this is that we have a special data section .maps BTF, a bit of BTF information. Now BTF has so every type in there has a number, and they refer to each other. So we can actually rearrange this around this data section, and then we would get something like this. So we say, okay, we have a data section .maps, and we have one map in there, which is one variable in this case. It's a global map, and it has this structure. And we actually, so there's this very rich type information about exactly what your key looks like. So you can have three structs deep, like keys that are 3 structs deep or very, very complex, and it's all expressed here. And we use this to actually infer all of the things. And there are a few tricks that I can't go into the details, but for example, here we have the type ID, so the type of the map, and we actually encode with an array, which with a pointer to an array, we encode like literal integer values. So it's a little complex for the types, but for the constants. But for your actual type information of the keys, it makes a lot of sense. And all of this is also passed to the kernel, so the kernel will also have all of this information. BTF types, so there are a couple of types of them, of BTF types. It's a little complex. We don't have really great vocabulary, but so there are a few kinds of these types. All of the type information is the integer, everything is a number in the end, right? So everything is an integer, and then you can describe what kind of integer, make an array out of integers, make an array out of structs. It's all stacks on top of each other. We have a few declarations, like is this a forward declaration? Is it a function? Is it global variable? Stuff like that. A few additional quantifiers, like is it volatile, constant, restricted? And we have a few tagging options, which are more advanced eBPF structures, but you can basically add annotations to your types, and then you can read them, for example, in user space to do interesting things. We have BTF, but there's also extended BTF, because we didn't think of it when we created BTF initially, apparently. It has this special structure, and what it has is func info, line info, and core relocations. And actually, I'll go into these a little bit afterwards. But just know that they're there if you see it. And these are actually really useful, but they use, they leverage the existing BTF thing. So if you have offsets in here, it actually references to offsets into the original BTF blob. When we load this into the kernel, we actually only load this whole BTF blob that we get almost one-to-one. So there's really not a lot of work in this case needed. The only thing, only if you actually want to understand how it's packed, you need to do a few things. And then once we have loaded that BTF, we had all of these numbers. But these numbers it's technically optional, but nowadays you will always want to do it, provided as when you're loading the maps, you're telling the kernel, hey, this is the ID of the key type, this is the ID of the value type, and this is the file descriptor of the BTF where you can find these IDs in. And the same goes when you load a program. So when you load a program, you say, hey, this is the BTF ID for my program, or this is the BTF ID where you can find a bunch of stuff about everything that's related to this program. And there's also the file, the func and line info. So the func info is for every function. There's one description, and it's like the line of the function, or how the function is called, and where it is, at which location it is. So this is something that we actually have to generate. So we have to when we make combine all of these functions together, we also have to make sure that these instruction offsets are good, and they're actually used for a lot of things. So BPF to BPF call validation, for example. So at some point, the kernel decided to do it out of order, so you can validate instructions or functions you call before the actual entry point. But to do that, you have to always make sure that you use the right amount of arguments, that they are correctly set. They're also used for callback functions and for a very interesting feature which is called freplace, where you can replace global objects in the kernel. So you can actually replace an eBPF function with another eBPF function, and it gets really mad. But look it up afterwards, because you can do really interesting things with this. And the line info is the blue stuff you see. So whenever we dump our program and we loaded our program with line info, you can actually see parts of the source code together with your with the decompiled instructions. So it's really useful for mainly debugging to see so this is what is actually the eBPF bytecode that got generated from a certain line of code, for example. And the yellow bits are the func info, by the way. So these are so that's useful for repack. So what we actually end up with in ordering is something like this. So one ELF file can contain multiple programs and multiple maps. But only one BTF, and you always load the BTF first, so you can provide the file descriptors to the maps, and then you can provide the file descriptors of the maps to the programs. So you have a sort of ordering in which you can load, in which you need to load things to get it all to work. So the next thing I would like to dive into is something called core, which is really useful for anyone working with probing, K-probes. So if you don't really need this when you do network programs, but if you go inspect kernel internals, then this is very useful. And before I dive into what it is, how it works, is explain the problem. So let's say I have a K-probe and I installed it on TCP close, and I want to then record some very specific parameter. So in this case, I want to record the cookie counter. But it's actually nested quite deep in this kernel structure. So this would be how you might originally do it. So I read this from the kernel, and then I push it onto, in this case, a perf event buffer, which is basically just a one-way street where I can push events to user space. So this might work if you run this on exactly the same machine that you compiled it against. But the moment you compile this on your kernel in 5.9 or 5.19, whatever, and you try to run it on anything else, and this structure changed in any significant way, then this doesn't do what you think it does, because the compiler just translates all of these names into an offset. But that offset changes. So how do we deal with compiling our, so how do we fix this? Is we can use core, which stands for compile once, run anywhere, everywhere, sorry. There's this really good blog that explains, that goes in way more detail than I ever can on how to actually use this. But I wanted to do a very brief overview of it. So there are these bunch of these macros where you can, so the most important one that we're going to look at today is this core read macro. But there are also a few other ones where you can, for example, say, hey, does this structure have a specific field, or does this enum value exist on the current kernel? And then you can actually dynamically create logic that only executes on certain kernels under certain circumstances, etc. But actually, if you go look at how this works, it all boils down to a few of these compiler built-in. So we extended the Clang compiler to understand these, and whenever it sees, I believe this is not extensive, by the way, but whenever it sees these built-ins, it actually generates these core relocation entries that I had shown before. So how do we use it? Is we just replace our helper function to read from the kernel with this macro, and instead of, and this is actually like an how do you call it, a variadic argument list. So we can put as many arguments in here as well as we want. The only thing to remember is that basically you replace your arrows with commas. It's just how this macro works. But what this macro does is it still generates the same. So on the right side in the comments, it's basically what this translates to. So we still use the same probe read kernel, but it generates a little bit more for us. It automatically adds the size of, etc. It returns the value, but it also inserts this built-in preserve access index built-in. And what this does is not much, so it still does basically the same thing. So if you, I'm going to walk you through this. So this is a translation of this is like the decompiled instructions. So the move instruction isn't important. On one we load X memory double width. So this is actually the loading of the sock pointer, the SK pointer, because reasons that I won't go over. And then from that socket pointer, we need to jump a bit down. In this case, 104 bytes to get to my counter. And that's all calculated based on how many fields are in between this counter and the head of the structure. But what we also have is a relocation entry, which exists. So what this relocation entry hints to us is that, let's say that I was accessing, I have some random structure and I was accessing field C, then it would encode 16-byte offset. But in our target, it is actually 24 bytes offset because someone added a field in between there on this new kernel version. And what this relocation entry is going to tell us is the name of all of the structs, so it knows which fields we are referencing and which struct, how deep. And we have a little bit of magic, which is called VM Linux. I actually have that a little bit out of order. So VM Linux, this is a big blob. We will coordinate to make the slides available somewhere, but this is interesting for later. So this is a little bit of logic to actually use one of our CI kernels and extract the VM Linux bit out of it. VM Linux is the ELF file that actually is the Linux kernel. So it's like the Linux kernel in an ELF format. And it also has a .btf section with all of the types that this kernel has. So if we inspect it, this particular kernel has like 90,000 unique types in it. And we can actually read this. So when we load a program on a target, we read this VM Linux and we see, hey, we can see that there's this difference, that there's this field added. what we then do is it's actually based on the name. So you have the name on the original one and the one and the name on the new kernel. So when you do name changes, there is a possibility it's still there. You can still make it work, but it's a little bit difficult. Again, referring to the guide on core that I mentioned earlier. But what happens is the loader looks up all of the every kernel that's named SOC in this case, and it might be one, it might be multiple, depending on how good the kernel people are naming their structures. And then we actually have we find we go look in all of the structures, and we do a sort of game where we give them scores based on all of the relocation entries, and the destination type that we find that matches the best to the one that we knew, that's the one we're going to use. And if we end up finding a type that is perfect for 90% of our relocations, but there's just one that wouldn't work, then we poison it. So we, if that instruction were to run, it actually crashes on the verifier. That sounds really dramatic, but you can actually use these conditional, so these questions you can ask as well, like does this field exist, to then make sure that code that would call it is actually that code. So there are tricks, but it's a little bit advanced. But what I want you to remember is that the loader can use the BTF, and the difference in BTF to do a bunch of these things, like know what the change a byte offset, or change the value of an enum, or change actually even how much you shift certain bits in a field before you use it. So when we actually, the slide I showed before was extracting the VM Linux out of basically a kernel ISO or a kernel image. But you can also, if enabled, you can access the BTF blob of your current VM Linux on this syskernel BTF VM Linux path. And when I ran it locally, I had a little more, I had more types than in my CI environment. But it's all the same idea. And actually, if you go look in this directory, you'll see that every kernel module, or nowadays it should be every kernel module that's compiled with your kernel, actually also has blobs of BTF. So you can also attach use core with functions and types that are not in the main kernel, but that are in some kernel module. The way you would use it is you can use this BTF tool, which is really great, to dump this file as well. Let's say dump it as C, and then you'll actually see that it will translate all of that BTF information back into C. So you can actually, when developing locally, you say, generate a VM Linux for my local machine. It gives you all of the types, and then you have access to all types. You never have to copy paste from kernel sources or whatever. Every data, every type that is available in the kernel, you can access them as well. So it's really convenient. So next, kfuncs. Kfuncs are cool. Kfuncs are basically the replacement for helpers. So when you start and you think you know helpers, then you also got to remember that you have to learn even more after that. We started since kernel 6.2, no more helpers are added, and the reason behind that is somewhat political, but it's just a reality. So after if you're looking for some functionality and you can't find it in a helper, go explore kernel for kfuncs. And basically what the idea is about kfuncs is they're actual functions of the kernel. So instead of writing special purpose kernel helpers, we can actually just designate an existing kernel function and say you're callable from eBPF now. But of course, we have to do some magic in the loader to make that work. It requires BTF, so there's a bunch of different ways or a bunch of different logic to apply here. Choose BTF, and you can also use core-like logic to also check if these exist, for example, or not. So you can actually then query the pointer to a kfunc and see, is it null? If it's null, then it's not available on my current kernel, which is just possible. It looks something like this. So normally you get this from libbpf, I believe, but you can also define it. Anyway, what we do is we say, okay, we define this ksim attribute, and we put this, so any function with this, we should put in this .ksims section. And then we say, okay, these are external functions. So we define them as an external function, and they should live in the ksim. And what you literally do to use the kfunc is you have to know what the signature of the function is, and you have to include it and make sure that it matches the kfunc for the kernel you want to call it on. And then you can use it just like any function, any helper you would otherwise use. So then you thought, now I learned how the section attribute works. And we go look, and there's no .ksim section, and that's because, of course, everything is special. If we go look up, there's still a relocation entry, but if we go to the symbol, it says, yeah, it's undefined. It's in an undefined section. And that's because we need to look for it in the actual kernel code, right? We're referring to a kernel function, not to something that we provided. So what we then have to do is, so I dump, again, this is the BTF information for my program, and this is the function that I provided. So I basically provided the description of, I want to call this. And then it's up to the loader to go find that in the kernel and go find what that actually is. And in this case, I found it in the NF contract. So these K funcs are not defined in the main VM Linux, but in this contract blob. And then, and if you go look here, it is actually loaded as like the 108th BTF bit of information on my machine at the time. And I need both the ID, or I need to have this ID to load the BTF blob back in to get a file descriptor, and I need this number, the number of the BTF, the BTF number here. And what I then can do is there's this magic, but it's this field called FD array. So I can provide an array of file descriptors, in this case, the file descriptor of my module. And then I don't have a slide of this, I believe, no. So then in the code, we actually have a call instruction, just like I showed at the very beginning of the presentation. And in this case, instead of just putting the number or like putting a relative address there, I put the file descriptor or the index into the file descriptor array in the offset, and then in an immediate value, I put the ID of the BTF, and then the kernel knows, sure, you are calling like this specific function in this kernel module. And the verifier does a lot of magic, turns that into an actual callable memory address, etc. But we have to still like combine all of this stuff. So we finally did like use every advanced function in eBPF, put everything together. We loaded our program, and now we need to attach it, right? Cool. How do we do that? Well, it depends, because nothing is easy. So we have sockets. So for socket filters, which are like, I believe, the very first program type, we of course attach it to a socket. And what do we use to attach it? We use an IO cuddle, so that's a different syscall. And then it's attached to the socket. Whenever we close our program, our socket is no more, so our program also unloads automatically. With kprobes and uprobes, and they actually attach to a perf event. So like normally you have also trace points in the kernel, for example. These are existing places in the kernel, but in this case, we first need to use the trace file system to actually tell the kernel where it should create a kprobe before we can actually attach to it. So we have to first create a new kprobe location, then open a perf event for that kprobe, and then attach the BTF to it via the IOCTL. So there's a lot of work involved, and then in this case, when you close your main program, it also magically goes away, but you might still want the kprobe there, right? And the whole reason for that is because the perf event, like whenever your file descriptor to the perf event goes away, it's also ref counted, it goes away, your program goes away. You can fix that, I'll get to that later. But it's different again. So we have TC and XTP programs. They use the TC and the IP command respectively, and then use netlink underneath to do the actual attachment, and they attach to these other kernel things. But then when I close my program, they don't go away, because even when my program closes, my TC and my QDisk still exists, or my netdef still exists, so the ref count is still there. So if there's really asymmetric behavior between like all of the different program types, and then at some point we decided, perhaps we should start using this attach and detach BPF command to make it a little easier, but you still need to get all of these file descriptors to these weird objects that have their own mechanisms again. And this is all hidden behind this loader. Like if you use a loader or use a loader library, loader will tend to do all of this for you. You can just say, attach it to this thing, and then just figure out how. But there is hopefully one solution, which is links. So the idea behind the link, which was added in 5.7, is that instead of having all of these weird APIs, let's just create one API to rule them all with an asterisk, which I'll get to. And then support was added gradually. But this is, so if you're running on newer kernels, you can just use these links, and they're really nice. And the cool thing about the links is the links, as long as a link exists, it holds a reference to both the attach point and the program itself. So you don't have to do a bunch of things, and you can, and they're just a BPF object as well, just like a program, just like a map, just like a BTF blob. So it's the fourth one. It's reference counted, so as the moment no one knows about it anymore, it's automatically collected and removed. And it's pinnable. And so pinning is one of the syscalls I mentioned at the beginning. You can actually take any of these BPF objects, and you can attach them to the file system. And then the files, as long as that fake file exists, it will hold on to a reference to a program or a link or map, whatever. But you can, and the links actually are like a layer above too. So the moment you can actually delete the link without deleting the program, and that detaches the program at that point. So it's technically a neater API. It also has additional features. So it has BPF cookies, which basically you can give every the same. So you can use one program, you load it once, attach it at 20 places, and give every location its own unique number, so you can resolve at which actual attachment points something was called. So you can also attach multiple your program at multiple locations with one syscall, but you can also have, for example, for XTP, sorry, not for XTP, but for TC, we now have a new API using the links, where you can actually have multiple programs attached on the same location in a neater way, in a way that was not possible before. But it's not all perfect, unfortunately. So here we get to the asterisks. So it's not the perfect API to rule them all, because struct ops. I won't go into details, but also look them up. They're really interesting. The ideas that you can implement kernel logic with BPF programs, like schedulers or other algorithms and so on. But you still have to do a whole bunch of a whole song and dance with the special BPF map type for specifically this program, and then linking it. Kprobes and uprobes and traceprobes still need a perf event, so we're not get rid of the perf event. The only thing is we get rid of the ioctl, so you still need to do some magic there. A bunch of programs are just not loved enough, so the kernel developers never decided to actually implement link support, like LWT programs or socket filters. Apparently no one uses them, so why bother implementing stuff, is, I imagine, their thought process. And then in 6.3, someone had the brilliant idea to after that reinvent a new way to attach programs. So there's this there's a way to implement hit drivers, so human interface devices, mouses, etc. in BPF. But in order to do it, so you first write it, you have to create a second program that is a syscall program, which is not to implement the syscall, but it can call syscalls. So you have like the second special program type that then acts in the kernel, uses a special k-func to attach the program, and it's total madness. And then it somehow creates a link in there and passes it back up. So the job of loader libraries is not yet done to hide all of this stupid complexity from the users who just want the hit driver. So we're getting pretty much to the end. So a lot of these, I've talked about a lot of features, and a lot of these were like introduced over time. So how do you know how to use X, Y, Z? So initial reaction would be use a kernel function, a kernel version number, like, oh, it was added in 6.7, so why not check whatever the kernel reports? Because the kernel lies. Well, not the kernel, but distros. So there are a bunch of these distributions that basically create backports and patches and a whole bunch of stuff, and then not update kernel versions because they are made by the kernel project, right? So especially, for example, the example that I'm very familiar with is RHEL. So there's RHEL 8.6, which is based on the 4.8 kernel, but it actually has like 5.4 BPF features. So you just can't rely on these version numbers. And actually also like an anecdote, I wasn't there to witness it, but apparently like 15 years or like whatever years ago, whenever we switched from kernel 2.6 to 3, I believe, apparently like user space everywhere used the kernel function, the kernel version number, and it broke like a lot of user space applications. So long story short, don't use kernel versions. It doesn't work. But what does then work is probing. So, and it actually is really stupid, but probing is literally try and see if it works. So whenever we, for example, cilium eBPF loads, like before it will actually load a program, it will actually then say, okay, you're trying to load like an XDP program, right? Or perhaps something more complex. So what it then does is it creates this XTP program that's basically empty. It just returns 1 or whatever. So it's like 2, 3 instructions. So it can't fail unless unless it's something to do with the program type. And then when that fails, it knows to report, hey buddy, you're running on a kernel version that doesn't support your XTP program, instead of it's so that's a way to eliminate that specifically that is the issue, instead of like one of your program itself. Because the kernel just returns, oh no, talking too long. So anyway, the kernel just returns like an error code, like something went wrong, but it often doesn't tell you, or at least not in a programmatically very easy way to figure out what went wrong. So what we do is we attempt to like, for the most obvious things, we have probes, and then we can return nice error messages, but these probes are also available for you. So if you, for example, say, oh, I know that I implemented some function that only exists on newer kernels, then you can call the probing functions that are provided by the library, ask the library, hey, is this there or not? And then in user space, make the decision, do I load my legacy eBPF program or my new eBPF program? Or you can even like go a step further and start modifying stuff there, or providing that information to your eBPF program via maps, so they can do it on runtime, for example. So that's just really useful if you ever get into issues with this. So probing together with core can basically resolve any compatibility issue you may have. And that's all I have to tell you for today. So are there any questions?
What a great talk. Thanks a lot. Any questions?
I see a hand there in the back.
Yep. I also see this hand.
Thanks a lot for the talk. I have a lot of questions, but I'll ask just a couple. At first, I have seen that you, across the talk, you've used LLVM-based tooling.
Yeah.
So am I right that if I'm a GCC fan, that all this tooling is available for GCC ecosystem too, for BPF programs?
So as far as I know, there is GCC tooling, but it might not be up to date with everything. So I mentioned, for example, there are nowadays there are quite a few changes or optimizations, for example, that I know that are made in LLVM specifically for BPF, and I know that there is a backend now, but it might not be like one-to-one compatible, like it doesn't do the exact same things as Clang does. So yes, there is one, and there's people working really hard to make it work and compatible, but I believe it's currently not 100%.
By the way, what kind of BPF specific optimizations are implemented in Clang?
So one of them I know, for example, Clang doesn't, or the BPF doesn't do like you can't store kernel or function pointers in memory, so you can't like call to a register. You always have to call to a relative memory address. So what happens in LLVM is whenever it detects that it wants to do that, it like compiles, like changes that invocation, compiles it out, and there are a few things around the way that the stack, the kernel stack is handled. So it uses like special, I believe it like translate into BPF specific byte code for certain load operations and so on.
Are there any Clang LVM optimizations that are disabled specifically for BPF target? For example, LTO.
Oh, that's a good one. I don't know that one. I didn't. It might be the case. I believe it's mainly add BTF specific passes whenever the target is enabled. I don't know if they. I also don't know if LTO is would be supported. So normally it's really unusual to link multiple eBPF programs.
Yeah.
Because it's actually, I know that, for example, BPF tool does it, but I don't know if it works on like the Clang level. So that would be a really cool thing to experiment with.
Yeah, that's why I'm asking it.
Yes.
And the last question about feature probing. As far as I understand, it should be pretty easy to implement a kernel module that does this probing for me and exports the results of this probing via some interface to the user space, where I can grab it in some like JSON format, something like that, instead of you doing a probing on my side.
Yeah, but that would, like, using a kernel module does defeat using eBPF a little bit. But
yep.
It does work. If you don't like writing probes yourselves, for example, I know that BTF tool actually has the capability to also like it does like bunch of probing up front, and then it just generates a JSON output for you. So you have to do it once, and then you can store that output somewhere, so you don't have to do it every time your program runs. So there are some options available, but BTF tool also just uses libbpf underneath to do all of these probes.
Great, thank you.
Yeah, you're welcome.
Any other questions? They might be not that hard as the previous ones. No? Okay, thank you so much, Dylan, once again.
Thank you.
Team who helped to organize everything, guys, help. Thank you so much. They were struggling for 2 days to make the sound, to make speakers sound more or less decent. A big shout out to the team which helped here with Networking Zone, Alona. And please remember her, because she will be driving you like driving you to the networking party. I will join you just a few minutes later. You have all just received the email, right? This is a mail with a feedback form, and I kindly ask all of you to fill it in. It would be really appreciated. Guys, can you please turn on my presentation here right now? Would you do that? And while you are filling in thanks. No. The biggest shout out goes to On the Spot. Thank you very much for hosting us, for making the events happen, for opportunity to bring such amazing speakers in Warsaw, to making a live stream, and to supporting TechSpot. Thank you very much. And now we are done. Thank you guys. Bye for those who were online with us, and let's go partying. Yay.